Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem palindrome partitioning from the SD sheet. But before we move on to the problem, if you guys are new to our channel, please do consider subscribing to our channel. So the problem states that you'll be given a string S and your task is to partition S such that every substring of that partition is a palindrome. So you need to return all the possible palindrome partitioning of any given string S. Now you know what is a palindrome string, right? A palindrome string is a string that reads the same backward as well as forward. So if you take this example where S is given as AAB, so you can say that you can have two kind of partitions where you can have one of the partitions as A, B, while the other partition can be A, and B. So you'll get this string. So you can see that the size of the string can at maximum be 16. So that actually gives you an idea that you can write the brute force of generating all the partitions. So let's take this string. So if you take this string, the possible answers can be, you can decide to have a partition here, then a partition here, then another partition here. So if you decide to have these kind of partitions, you will end up getting the string A, B, B. So this can be the first partition. And the other partition can be, you just decide that you are gonna have a partition over here and then over here and nothing else. So this will give you A, and B. Now suddenly you can also think of having the partition over here, then another partition over here. So this will give you A, B and B. Now all of these substrings are palindrome. So you can have this partition as comma, B, comma B. Here is that all the substrings that you're partitioning are palindrome in themselves. Other partition that you can try to do is you just put a single partition over here that will give you the string A and B. So you can try out all the other partitions and you'll only get these four partitions as your possible answer. So this is what the problem states. So this is the first list of all the substrings. This is the second list of all the substrings. This is the third list where this is the fourth list. And your task is to return a list of all of these lists that are possible. Since Unacademy has sponsored this video, let me tell you something about them. Now they have brought this subscription plan of enrolling for learning competitive programming. Now why should someone take the subscription plan? First of all, when you take up a subscription, you get access to all the batches and courses that are running currently, and also the ones that, so it's not a particular batch or course that you're paying for, you're actually paying for all the content that is present on their platform. Also, you can learn from your favorite teachers and be part of the courses and batches that are being taken up by them. They're also providing you with dedicated doubt sessions, yes, where you can ask your doubts in live classes. You also have the option to interact with the teachers directly in the live class through messages, emojis, whatever you want to. And yes, there are different types of batches and courses starting and running at all times. So if you're at a beginner, intermediate or advanced level, there are batches and courses running relevant to your need. So these are the things that you will get if you take up the subscription as at Unacademy. Now soon there is an interview preparation batch starting on 24th February, especially for intermediate level folks, which will help you get ready for upcoming placements. Now this batch is being taken by Deepak Gaur and Riya Bansal. You can see Deepak Gaur was a ICPC World finalist and Riya Bansal is currently working at Flipkart. So yeah, do check out the batch by clicking on the link that is given in the description. And if you want any discount on the subscription, you can use the coupon code TakeYouForward to get that discount. So how can you solve this problem? Obviously, we have to write a brute force that does generate all the partitions. And some common thing to observe over here is whenever we are doing a partition, every substring has to be a palindrome. And the partition can be anywhere. So it's basically, you have to write a function that does the same thing again and again. And you know, whenever you write a function that does the same thing again and again of partitioning strings, that is when you start thinking of recursion. So how will you think of recursion? So what is your task? What is your primary task? The primary task is to partition. Okay, so let's do it step by step. So what if I ask you, which is the first position where you will partition in order to get a substring, that is palindrome? Your answer to that will be, you'll try partitioning over here. Yes, so if you do a partition over here, you will still be left out with a substring ABB. But since you've partitioned here, this string, this substring is a palindrome. So that's your first thinking. Where can I have the first partition? That's over here. Now what if I ask you, if I don't allow you to have a partition here, then where can you have your second partition? Now the answer to that will be, you can have your second partition over here right after A. You can do a partition. Why? Because this double A is a palindromic substring. So if you do that, you'll be still left out with a string BB, for which you have to do a partition. So can you do a partition over here? The answer to that will be no, because if you do a partition over here, this substring in itself is not a palindrome, and what you require is, whenever you do a partition, the substring should be palindrome. So thereby you cannot do a partition here. Can you do a partition here? Obviously not. Why? Because AABB is not a palindromic substring. So we cannot do a partition here. So we can see, whenever we started, we could only do a partition over here and a partition over here. So that is what we do. We try to do a partition wherever it is possible. So when we have done a partition here, we are left out with this string. So let's call a recursion for this string only, that's ABB. So now if I ask you, where can you do a partition in this ABB? Your answer to that will be, you probably can do a partition right over here. Yes, right over here. And that will give you something like this. If you do a partition here, this substring in itself is a palindromic substring. So you'll be left out with a substring BB. Now what if I ask you, what is the next index where you can do the partition? Can you do a partition over here? Can you do? No, because this substring then will not be a palindromic one. Can you do a partition over here? Again, no, because this entire substring will not be a palindrome. So the only partition you can do will be over here, and you do that. And after that, you tend to call the recursion for the remaining substring, that is BB. Now my question to you is, where can you do a partition? Can you do a partition here? Yes, you can do it. So if you try to do a partition there, what you get is A, right after that you do a partition here. So this substring in itself is a palindromic substring. After that, you are left out with the substring B. For that, you again call a recursion, remember. Now, since you did a partition here, my question to you is, can you do a partition right here? Yes, you can do that partition. And if you do that, what you'll get is A, A, and since you did the partition at the end, you will get BB. Now this is a substring in itself. Now since you were able to do the partitions in such a way that at the end, you put a partition at the end. So that is where you stop. But let's wait. Let's do the left part first. Where's the last partition that you did? Right over here. And you're still left with this substring. So let's call a recursion for this substring. Now when you call a recursion for this substring, it decides where to do the partition. So can you do a partition here? Yes, you can do that partition, because if you decide to do that partition, you will be again doing a partition at the end, and that will make sure that this substring is a palindrome. And since you are able to do a partition at the end, that means this substring, this substring, this substring, and this substring, which is nothing but A comma A comma B comma B, is a partition where every substring is a palindrome. So this, whenever you reach the end, remember, whenever you reach the end, your recursion call is over. So now it's time to get back. So that's backtracking. So make sure you get back. And whenever you get back, you can say that this recursion call is also over. So you try to get back. Now this recursion call was left out because you always call the left recursions at first. So this recursion call was left. Now whenever you call this recursion, a partition was done at the end. So whenever you do the partition at the end, what does that signify? That means you were able to partition in such a way that this A was a palindrome, this A was a palindrome, and this BB in itself was a palindrome. So you basically get another list of substrings or another partition where all the substrings are palindrome. So you can again store it in your list of substrings. So this recursion, I can say, is over. So it's time to get back. So I can say I was successfully able to do the partitions from here. So my job is done. So the recursion for this is now over. So I get back. So since I get back and I see that there are no possible other partitions apart from this, because you cannot partition here, you cannot partition here, because all the substrings will not be palindrome. So this recursion is also over. So you try to get back. Now since this left recursion call of partition is over, we come out and check for the right. So the right has a partition over here. So it calls a recursion for this now. So whenever you have this BB, where do you want to partition at first? The answer to that will be you'll try to partition here. Can you? Yes, you can, because if you do a partition, you will have right here B, and that's a palindrome. And you'll still be left out with a substring B, yes, for which you'll call a recursion. And the other partition that you can do is right here, and if you do that you will get A and a B and a B and the partition at the end. But this recursion will not be called as of now. You'll call this recursion. Now where can you partition? If I ask you, you'll try to partition here. Can you? Yes, you can. So let's do a partition there. So if you try to partition it over there, you will get it as this. So again you're able to do a partition right at the end. And if you're able to do a partition right at the end, that means you're able to generate a partition that has all the substrings as palindrome. So I can call these substrings as palindrome. So this will be another answer of mine. That's A, B, and B. So I can store them in a list of strings. So this recursion can be said as being over. So once this is over, you can try to get back. Now this cannot have any further partition, so this recursion is also over. So we get back. Now it's time to execute the right recursion. So when you execute the right recursion, you see that the last partition was done right at the end. So whenever you do the partition right at the end, that means you're able to generate a partition where every substring was a palindrome. Over here AA is a palindrome and BB is a palindrome. So I can say that this can be a part of my answer. So I simply take it down. So this recursion is also over. So we try to get back. So now all recursion calls for this substring BB is over. So we get back. So ultimately I can see I was able to partition AABB in such a way that I got all the 4 partitions, which could be my answer. So this was the recursive tree that I did show you. But now it's time to convert this into a pseudo code, because if you don't convert that into a pseudo code, you cannot write your code. So basically, what do we see at the first? We have a string. So we can say our recursive function for sure will have a string. What next? We're actually trying to partition it right from here. Then we try to partition here. Then we try to partition here. Then we try to partition here. So it's basically saying that for every string, I'm starting at a given index. So I can say this is 0, this is 1, this is 2, this is third index. So I'm starting from the 0th index. And what I'm trying to do is, if I'm able to partition the 0th index, that was the case, I was able to partition. If I'm able to partition on the first index, that was the case over here, I was able to. And so on, I will see, will I be able to partition all the index, which means I'm actually looping. Yes, I'm looping. I'm looping and checking if a partition is possible. And if I was able to partition here, I basically take the substring right from the 0th index till the 0th index. That's a substring I take. And I call the recursion for the string starting with the first index, because now the string starts with the first index. Similarly, if I'm doing a partition on the first index, then I'll take the substring 0 to 1, very very crucial stage, because you're taking AA. So that is meaning you're taking 0 to 1. So you take that substring, and where will you call the recursion from? You'll call the recursion from the second index, because you're left out with the string BB. So that's the second index where you call the next recursion from. Similarly, you cannot do a second partition, because if you partition here, this is not a palindrome. So make sure whenever you're trying to partition on the 0th index, please do check if 0 to 0 can be a palindrome, if 0 to 1 can be a palindrome. Similarly, if you're trying to partition from 0 to 2, that means 0 to 2 has to be a palindrome, which was not the case. So you'll not partition. Over here, 0 to 3 has to be a palindrome. Again, that's not the case. So you don't partition. So basically, I can say the generalized version will be there will be a string, there will be an index, and there will be a looping that will go on from index right till the end. And so when will you be able to partition, assuming that I is 0, 1, 2, 3? I can say if index till I substring is a palindrome, then only I'll be able to partition. If 0 and 0 was a palindrome, if 0 1 was a palindrome, if 0 2 was a palindrome, then only I can call the next recursion and again try the similar way of looping. So this is gonna be your pseudo code. I'll show you the code and you'll start understanding it in a much better way. But this is the generalized version. And what is the base case? Whenever you reach the end. So whenever you reach the end, so that means whenever you reach the index as n, I can say whenever your index reaches n, that means you're able to partition everyone, and all these substrings would have been stored somewhere, and you can store them in your ultimate answer. So once you see the code, you will start getting a better vision of this. So if you look at the Java code, you have to return a list of strings, which will be answer, and you are given a string s. So initially, let's have a list of strings, which will be our answer, and let's have a list of strings, because you're generating a string every time. So at the end, this is a list which will be generated. So for generating this, let's consider this path, okay? And we are gonna start the recursion from the index 0 and the string s, and we are carrying these two data structures, which one of which will store this entire stuff, and all the lists generated will be stored in this result 1. So s and index 0 is where we start. So we can see that a function starting from index 0 and s has been called. And the base case will always be whenever you have done the partition, right? Whenever you have reached here, which means you have reached the index n. So when you have partitioned it completely, you can say that this list which is generated, which was the path, you can store this in your ultimate data structure, that is the res. So we store it and we break out. So this is a base case. Base case is very clear. Now what about the partition? So you try to partition from index, right? Like over here it was 0, so you try to partition from 0, 1, 2 and 3. Like in this case it was 2, so you'll try to partition here and you'll try to partition here. That is what has been done. So we try to partition. So that's why we start from index, right? And we go on till the end. And what do we check? If we can partition 0, we need to check if 0 and 0 is a palindrome. So that is what we check. If the string from index to I is palindrome or not. So if that is a palindrome, what do? Is I take the substring. So basically I take this substring A and store it in our list, which will be this ultimate list, and I call the next substring right from index 2. So that is what I'm doing. I'm just going to the next I plus 1, because if you have done the 0 to 0, so the next one will be from 1. So that is what I call, and I pass on the string, path and res. Now please make sure you remove when you backtrack, because just assume, yes, just assume that you have done a partition here. So that will create this individual string into that list. But when you go back, this B has to go off from that list. Otherwise, you'll not get a BB. So please make sure you take that B out. So that is what we have done it over here. So this will be the entire for loop. And you know how to write this as palindrome function. It's a simple palindromic check function. I'm not going to explain it. Simple, start from the start and have a pointer at the end, and basically keep on checking till they don't cross. This is how you check the palindrome. So this will be the entire recursive function that generates all the partition substrings as the list, and that is gonna what and that is what we are gonna return. So that was about the Java code. So let's talk about the C++ code. So you have to return a vector of strings, that is a list of strings, and you're given a string s. So initially what we do is we create a result vector which will be our answer, and we also create a path. Now what is this path? This path will be storing the individual list of substrings when you do the partition for every recursion. And what is this res? The res will be storing all these guys. Yes, all these guys will be stored in a data structure res. So that is what res is all about. So you know you have to start from the 0th index, that is what you have started, and you have the string and you pass both the data structures. So initially we all know that the base case will be when you have done the last partition, right? That will be the base case. So we can say whenever our index reaches the s dot size, that means you have done the partition. So this entire stuff will be actually path, right? That will be a list of strings, that is path. So you insert that into your res. That's basically the ultimate list of strings. So you insert that. Once you have done that, you return. So you've inserted this entire list or this entire list into your res data structure. So if that is not the case, if that is not the last partition, so what do? You basically loop. And how do you loop? You know how to loop. If you are at the 0th index, that means you have a probability of partitioning here, here, and here, and here. So that is what you do by your for loop, right? You start from index and you start to a partition 0, 1, 2, 3. Now when can you partition? You can only put a partition over here if this guy is a palindrome. You can only put a partition here if this AA is a palindrome. So that is what we check. If you're able to partition, then the substring from index to I should be a palindrome, and I've written a function to check that. So we can easily check if that is palindrome. If this small 1a or if this double a is a palindrome, what we do is we take that substring. Like if 00 means a, 01 means a, if that is palindrome, so we're taking a, right? we are taking we are taking a, right? So we store that in our list, which is the path. So ultimately a will be there. So that is what I'm doing. I'm storing it. And once you have done the partition at 0, that means if you have done the partition here or if you have done the partition here, then we start from the next index, right? So that's why I call I plus 1 and we start the next index. That is what we have done here, the transition. So that is what we do and call the next recursion, so that it can start partitioning again. But when this function call is over and we decide to come back, for an example, we had a partition here, right? And this recursion call is over and now we are coming back. So you have to make sure that this b which was there in this path has to be taken out. So we take this b out. Yes, we take this b out from the path, so that the next time the partition can be done and we can take the new bb. If we had not taken this b, then this list would have contained b. Since path is a reference variable, so please make sure you do a pop back while you come back, so that this b will be taken out. So this will be the for loop which will make the partition, and this will be the recursion call which will make sure that the next partitions are done. Ultimately it'll reach the base case and it'll get all the partition substrings which are palindrome. So you know how to write as palindrome, so I'm not explaining this. So ultimately whenever this function call will be over, you will get your answer res which you can return. So guys, I hope you have understood the explanation as well as the code. So just in case you did, please make sure you like this video, and if you are new to our channel, don't forget to hit that subscribe button. So with this, I'll be wrapping up this video. Let's meet in some other video where we'll be solving the next problem from the SD sheet.